Hello. In one video, I hope to go over everything you need to know about using LDA when you do these enolate type of reactions. And the enolate chemistry I'm talking about is for aldols, or aldol condensation, and Claisen. Whenever you make an enolate, you can make an enolate with the LDA base. It's different than using OH minus or OET because you don't establish an equilibrium because LDA is such a strong base, and in my class we're going to be using it at equal molar amounts. There are tricks where you could use it at like 0.5 equivalents or less than 1 equivalent where you do get equilibrium, but in my class assume that you have a lot of LDA and you are going to rip off that alpha hydrogen completely, 100% of the molecules. What is the consequence of that? What is the consequence of LDA being very strong base? Well, LDA, as you remember, is lithium and diisopropylamine. So you have two lone pairs, and this is negative. It's a strong base because it comes from a weak acid, right? You remember that idea where the stronger the base, the weaker the acid it came from, or you can even say the strongest acids give the weakest bases. Anyway, the conjugate acid for this molecule, let me use a different color. Let's use blue. The conjugate acid looks like this, and that's a pKa equal to 36. So that is considered a fairly weak acid. So therefore, this is a strong base. Think about the alternative, right? The alternative is NaOET. So NaOET is Na plus, OET minus. So now when we do the acid-base reaction and we get our conjugate acid, see we have a pKa of equals to, I call it 15.5, some people call it 16. So that's a moderate acid. So this is a weaker base than LDA, okay? And the consequence of that is this. When you want to do an aldol reaction, let's use a simple aldehyde, and let's use our NaOET. Don't forget, you should have some proton sources, but not acid. Have the proton source as the solvent, so ETOH. You are making this enolate. Again, I like to draw the O enolate or the oxygen enolate. Okay, and the thing is, you have an equilibrium. So in real life, you actually have something like this. Let's see, like that. Okay, so yes, the majority is still the non-enolate, but whenever you have some enolate, that enolate will attack the non-enolate to give you your aldol product. So eventually you'll have this. Now, I like to draw the condensation product, or I insist my students draw the condensation product if they can. Not if they can, but if it's possible. And so all of this has been covered in previous videos, so I'm not going to go through it in too much depth here. But that should be your product. And you could draw the H there if you want, or you don't have to. Okay, so again, here's your equilibrium. Now, if you use LDA, by the way, do you know why that's the equilibrium? Because your OET minus became this, and that's a pKa of, again, 15.5. The pKa of an aldehyde is around 17. So yeah, it's slightly less acidic. So it does favor the left. Okay, and you establish this equilibrium. That's the important part for the aldol and claisen, that especially if you're doing a self-aldol, you need some of it, in this case the majority of it, as the non-enolate. Okay, all right. I think this is all second nature to a lot of you. I did mention LDA in class, and so why LDA? Because LDA, since it's such a strong base, your equilibrium is really far to the right, almost 100%. And so I would write something like this. Now, why would we want 100% of the enolate, right? I thought we want some of this to be non-enolate so we could have the attack. Well, this is very useful. If you could get this to be 100%, you would carry that forward with a second reaction where you could do a cross aldol. So let's say we have a different aldehyde. Let's say we have benzaldehyde. Oh, heck. Well, no, let's use benzaldehyde. I'll show you the beauty of LDA on the next one. By the way, yes, the conjugate acid now looks like this. Very weak. And remember, equilibrium favors the weaker acid. So if this is a weak acid, your equilibrium, I say it's close to 100%. Okay, I say it's close to 100%. And that's of these two. Okay. Here we're doing a cross-claisen, where we bring in another aldehyde or ketone, and our final answer is this. I am going fast because this is review. Claisen, cross-aldol condensation. Because this is review, I'm going through this part fast, and I'll slow down when I talk about how special LDA is. Right now, you could have done this reaction, right? You could have gotten this product here by just mixing these two. These two, and using an oxide base. That's your typical cross-aldol, where one can be the enolate and one cannot. But what if you want a cross-aldol where both of them can be the enolate? This is where the beauty of LDA comes into play, because if I tried to do something like this, for instance, that plus this. Okay, if I use NaOH, and we'll put water as the protic solvent, we'll get a mixture. Okay, we'll get, let's say we call this A and B. We'll get A attack B, A attack A, the enolate version of A. The enolate version of B attack B, and the enolate version of B attack A. Okay. So which one do you want? I mean, we could pick one randomly. Let's say we want this one right here. If I want this, I end up getting 25% each. If I do it this way with NaOH. Take a look at this trick here. If I want A to attack B, what I would do is I would make A 100% the enolate using LDA. Okay. Again, for my class, you are assuming that you have enough LDA to convert all of that to the enolate. And then we bring in our second molecule. Okay. Now, the attack, let me think about this carefully. The attack needs a protic solvent because we need to convert this to an OH, which will then be dehydrated. So let me give us, in this case it really doesn't matter, let's use just H2O. Okay? So what's the beauty of this? The beauty of this is that you set up the enolate and get this 100%. And then you bring in your other molecule, right? This was the H to O. So just so to be very, very clear, this first reaction, LDA, gives you this. The second reaction, we bring in our aldehyde, and we finally get this molecule here. Like that. Okay. That is a, let me do it in orange. That is A attack B. So in terms of what you can see, or what my class can see on an exam, they can see this. And you have to draw the product. Draw product. Okay. It's a cross aldol, okay? But because we do it stepwise, because we make the enolate first, and then we bring in the second molecule, I sometimes call it a directed cross aldol. And so again, as warning to my students, this is definitely a possibility, okay? A lot of times I will put temperature. You know, LDA is such a strong base that you want to control the heat a little bit. So sometimes I put negative 78 degrees C. I think that is, what is that? I think that's dry ice with acetone to make that cold slurry. Okay, so that's one thing you could see. The other thing is, well, okay, let me do the same thing actually. It's something very similar. But my starting ketone is now going to be this. Let's do that. Well, okay. When you do LDA, and I am going to put the temperature now for sure, you get what's called the kinetic enolate if you have two choices. And we do have two choices. We have the alpha 1 on the right, the left, and the alpha 2 on the right. Did you notice in the previous example, here we only have one alpha carbon, here only one alpha carbon, here only one alpha carbon. We have two alpha carbons, but they each give the same thing. So they each end up with the same product. So it doesn't matter which one you choose. And the same thing here. It's symmetrical. So it doesn't matter which of the two alpha carbons you choose to deprotonate. But in this case, you do choose. And you choose with LDA because it's strong and fast base. You go for the less crowded H. Go for less crowded alpha hydrogen. Okay, so it's the one on the methyl group. And therefore, let me draw what we get. You should be drawing just the kinetic enolate. We call this the kinetic because it's the enolate that's made faster. It's going to be the one on the right, the double bonds on the right. So this is called the kinetic enolate. The other enolate would be considered a thermodynamic enolate. And so let me be very specific. The kinetic enolate, you will assume that it's close to 100%. The thermodynamic enolate is the more stable, actually. And that's kind of odd that the major product is the kinetic, even though the more stable is the thermodynamic. I'm not going to get into the details of um, um, why, well, no. I'm not going to get into the details of the reaction coordinate diagram where we see, how high a hill you have to jump over to get to the kinetic versus the thermodynamic. I'm hoping that you can understand that because we have a fast, strong base, you go and we're running it at very low temperatures. Once you remove the proton, that's easier to remove, then you're done. You don't get another chance to remove this hydrogen here. This other enolate is called a thermodynamic, and you get none of that when you use LDA. Now, there's a disclaimer. You get none of the thermodynamic if you use LDA at least one equivalent and at these temperatures. Okay. So thermodynamic enolate, and you can all see that because our double bond is more stable. It's more substituted, and for an alkene, that equates to stability. It's more stable. But you get none of that in this case. Do you know how to get the thermodynamic enolate? You can get it if you use a weaker base. Can get this if you use a weaker base. Like what? Like NaOH. Okay? So one more time, I'll be very explicit. A possible problem could be this. Box here. Okay. And then let us use, we're doing cross aldol again. Okay, let's use that, and let's use ethanol to provide the proton in this cross aldol, directed cross aldol, if you want to use my terminology. Okay, another, you could use this with Claisen. So for instance, if you have this, I know that you've heard me and maybe other professors say, make sure your base matches the leaving group. But the thing with LDA is, LDA doesn't substitute, so you'll not get any saponification. You won't exchange this for LDA, so you don't get transit esterification. All the problems you see when you use the wrong base, like OH minus or OCH3 minus, in this case, yeah, then you'll run into problems because these two can attack here and kick out this leaving group. LDA is not, it's not really a good nucleophile. LDA is just a good base. So we are safe to use this LDA, we're safe to use LDA and not worry about those other side reactions. So just simply do what you know. You're going to make the enolate, and with that enolate, you could attack stuff. So if I really want to do a Claisen, maybe I could attack. Okay, so this is a tricky. This one, the ethyl has to match, but maybe if I do something like this, okay. The other thing is, you remember with Claisen, you have a second reaction where you have to reprotonate, and we have that. Okay, that's how my students will see LDA. Do you want me to fill in the products real quick? Okay. For the first one, we do have to determine kinetic or thermodynamic, and we're going to make the enolate, and we're going to go for the less crowded side. And so my enolate is going to look like this. It doesn't really matter to me, cis or trans. And then we attack. We use that enolate to attack. And we can do the condensation. And we have these two groups. Now, I did that pretty fast. That's only because I refamiliarized myself with the aldol mechanism, right? Remember all the tricks that I discussed before? You have a dot, here. No, not there. You have a dot here. That dot is here. And you have alphas, right? Here's your alpha you're going to use. So there's your alpha, there's your alpha. Okay. For the Claisen, again, you're just doing what you know how to do. You know that with base and an ester, you get the enolate. Okay, so do that. It doesn't, when you use LDA, it's okay it doesn't match. Okay, because again, you are, LDA will not substitute. LDA will not do transesterification. Let me swing this out of the way. Okay. So the other thing is this, and I've said this before, because you're using LDA, you get 100% of this. So there is no attacking another one of itself. There is no attacking another one of itself because you have 100% of this. That means you have none of this, right? So when you do a self-aldol or self-Claisen, you need a percentage of the amount to be enolate and another percentage to be the non-enolate. Here, we get 100%. And just to really specify, this is 100% of the kinetic. For the ester, you don't have kinetic or thermodynamic. You only have one side that has an alpha carbon. So we'll just call this 100% the enolate, or 100%. Okay? So there's no self, is basically what I'm saying. There's no self-aldol with LDA. Again, this is disclaimer because there are tricks to do a self-aldol with LDA if you run this at higher temperatures and you have less than one equivalent. But I'm trying to keep it as simple as possible. Whenever I use LDA, I am blasting it to get the 100% the enolate. You just have to draw the correct enolate. And for this one, the second one, right, because we have 100%, there's no self-Claisen. Meaning that we're going to have to bring in another molecule to make the aldol, another molecule to make the Claisen product. Okay, so the Claisen product looks like this. Remember, you kick out the leaving group of the ester you attack. So we attacked, again, the dot right there. That's the dot right there. Let's label the alpha, alpha, alpha. And so let's finish up the drawing. You remake the double bond, and you kick out the leaving group, but you still have this other junk on it, right? That's your final product for the crossed Claisen, or specifically the directed cross Claisen using LDA.